Ladies and gents, welcome to this week's Geotalk. I think you can all hear me, which is hopefully good. We have a relatively small audience here in the room, but lots of people online. So thank you all for joining us, both on Zoom and on YouTube. And most importantly, thank you to Alan Glazner for joining us to give this lecture. It's really a privilege to have you here, Alan. And thanks for offering to give this talk. And thank you to Race for agreeing to, for asking Alan if he'd give this talk. It's great to have you. And I hope Race is in the audience because I'm sure there will be some debate afterwards. So just before we begin, let me introduce the speaker. Alan Glazner is a distinguished professor emeritus at the University of North Carolina at Chapel Hill. And as a native of California, he studied at Pomona College and the University of California at Los Angeles. And as you'll hear in this talk, he is doing a lot of work on understanding magmatic systems and debunking some of the I guess, problematic hypotheses about magma chambers using both old and new data. And as a native of California, he's also passionate about the Sierra Nevada, the mountains, and has published several geology underfoot books about the eastern and southern California area, including Yosemite National Park and Death Valley National Park. So Alan, thank you so much for joining us. I'm going to stop the screen share here and open up to you to share your screen.
Right. That should be, are you seeing it now? Share, there we go. Okay, have you got the presentation screen?
We have the full presentation. We can hear you loud and clear in the room.
All
Our
right.
lights are off and we're ready for you to go. Alan, thanks so much. Over to you.
All right, thank you. All right, I'm very pleased and honored to be here or there virtually in South Africa and greatly look forward to coming back to South Africa to see more of the geology there. And what I'm going to do today is to talk about the concept of a magma chamber in petrology. This is a concept that is so deeply ingrained in thought about how igneous petrology works that it's really hard to step back and say, how much of this is justified based on what we know about magmatic systems today and how much of it is not. And the main point of my talk is that our picture of magma chambers that we all carry around in our head is quite probably wrong. Geophysicists can't find these things. There are geophysical reasons why it's very difficult to build a big magma chamber, and at least in granitic rocks, which is what the focus of my work is on, it's pretty clear that plutons that were thought to have been emplaced as large blobs of molten mobile magma were actually emplaced over long periods of time in small increments. They were assembled over millions of years in many cases, rather than just emplaced as a big blob of mobile magma. So what I'd like to start out with is I'm going to give you a blank screen, a whiteboard, and I would like you to mentally draw on this screen. I'll just give you a few seconds. Mentally draw your picture of what a magma chamber is like. So I think a cartoon probably pops into everyone's head that looks something like this. This is on the US government's National Park Service website, a volcano with a big reddish or orangish blob underneath it that's feeding an active eruption. This is a really interesting figure because it kind of looks like the crust is made out of wood. It looks like maple to me, and the volcano looks like a grape jelly sandwich, but this is sort of the idea, a big blob of magma at a very shallow depth. There's no scale on this, but this is, you know, a kilometer or two down there. And that's kind of the picture we have in mind. And again, as I said at the beginning, I'm going to tell you that I think much of this picture, at least for continental volcanoes, is incorrect. And I want to extend that a little bit to layered mafic intrusions in this talk. This sentence is the only time I'm going to say the word Bushveld in this talk. Not being an expert and not having visited it yet, I want to stay out of that, but I will talk about the Skærgaard intrusion somewhat later in the talk. I'd like to make an appeal for bridging across subfields within petrology. You know, we have geology is divided into various fields, and one of those is igneous petrology, and one of those is metamorphic petrology, and those are typically treated as two completely separate things. People that work on one rarely work on the other. The terminology is different, the classification is different, and so on. And that's how it's presented in textbooks. But that's not how the Earth works. Igneous rocks and metamorphism are very closely related, largely because igneous rocks cause a lot of metamorphism and get metamorphosed in the process. And then even within igneous petrology, there are many, many divides. And so here on the left, I've got a granite. That's the kind of stuff that I work on in the Sierra Nevada and elsewhere, mostly in the Western United States. On the right is a piece of ore from the JM Reef at the Stillwater complex in Montana, and there are good reasons to study both. The layered mafic intrusions, the stuff on the right, you can see various minerals, bornite, pyrite, and so forth in there. That's the US's largest source of platinum. Very good economic reasons for studying that. On the left is the stuff that the continental crust is made out of, or the rocks derived from granite or make up the rest of the continental crust. And so this is basically the reason the Earth has continents and how you make. The stuff on the left is actually not all that well understood and a topic of much debate. And I'd like to make a plea to get these two communities together. In 2010, we ran a conference in California where we got a lot of people from the layered mafic intrusion community, including Race and Sophia, into the Sierra Nevada, and we looked at things, and it was a really good discussion because I learned a lot about how people in the layered mafic intrusion community think about these things. It's a different angle, and I hope that some of them learned how we in the granite community think. And I think a really great field conference would be something to get these two communities together. Maybe we can organize something like that sometime. So I'm going to talk about magma chambers, and I want to start out by talking about magma because there is precious little consensus on what magma is, believe it or not. It's the fundamental substance of igneous petrology. And yet, if you ask two geologists what it is, you'll get completely different definitions, and a geophysicist would give you yet another one. I really like this definition from the Oxford English Dictionary. You can look this up. Definition number 5 is that magma is a confused or disordered body or mass of something, okay? And that kind of, the confusion and disorder, and it's a mass of something, kind of sums up the feeling I have for how we think about magma as a material that makes igneous rocks. I think we all can agree that this kind of eruption, this is Etna in 2021, is magma reaching the surface and erupting as pyroclastic rocks and lavas and so forth. It's mobile, it can move through dikes, it can move around, large distances and erupt on sort of volcanic or human time scales. But what about this? This is an experiment on partially melting a peridotite, and the red, I've false colored this, so the green are very olivine and other minerals, and the peridotite in the red is partial melt. And this is about 2% partial melt. Would you call it magma? Turns out a lot of people would. I would not call this magma. And after the example I'm going to give in a slide or two, my colleagues and I wrote an opinion piece for EOS, the American Geophysical Union publication, saying we need a new definition for magma, because I think that we as a community can get in big trouble if we keep using the term magma for things like this. So I'll give you an example of that a bit in a few slides. The first image I know of a magma chamber in a book is from Lyell, 1839. Principles of Geology. These were hand-colored frontispieces in these old books. And if anyone knows of an earlier image like this, I'd love to know about it. But this is the oldest one I can find. It's almost 2 centuries old. And Lyell shows the 4 great classes of rocks, and colored in red are magma and plutonic rocks that have cooled from them, and in blue are volcanic rocks, including an erupting volcano and so forth. So he's showing an erupting volcano being fed by a subterranean magma chamber. And this is the basis of that image that we all carry around. So this is a 1976 publication from the US Geological Survey on the Long Valley caldera, which erupted the massive Bishop Tuff 760,000 years ago. And at that time, they hypothesized, based on really not on data, just on sort of the axiom that these volcanoes were underlain by magma chambers. As you see, a contemporary magma chamber lying at a depth of 5, 8, 10 kilometers. We now know that's not there. We have a lot of geophysical data, and there's just nothing like that there. But at the time, that was the image. That's when I was in school, and I carried this image around with me quite a bit. The pictures have gotten a little more elegant looking now. This is a recent paper on volcanoes in Kamchatka, and you can see the orange-red blobs there are labeled as magma chambers. The coloring isn't presence or absence of magma. It is the P-wave, S-wave velocity ratio, as you can see on the scale at the bottom. And so the orangey stuff is a high VP to VS ratio. Magma will have a high VP to VS ratio because S-waves slow down or aren't transmitted through liquids. And so presence of some liquid slows the S-waves down a lot more than the P-waves, but so do fluids and so on. So here they've labeled these things as magma chambers at depths of about 1 kilometer below the surface. They may be, but just keep in mind when you see things colored like this, they're not coloring it because they drilled down there and found magma. They're coloring it based on some proxy, in this case, the velocities, seismic velocities. In 2015, the University of Utah Geophysics Group, Seismology Group, published a paper in Science where they talked about magma reservoirs and magma chambers under Yellowstone National Park. Yellowstone National Park has had 3 super eruptions in the past 2 million years. 1.8, 1.2, and 0.6 million years ago. So if you extrapolate that series, it sounds like, oh, we're due for one now. So they published this image of this lower crustal magma reservoir being fed by the Yellowstone hotspot plume, and then a gigantic magma chamber in the upper crust. And they released a press release that had the phrase, there's enough magma in this upper magma chamber to fill the Grand Canyon 11 times. A Grand Canyon full of magma is kind of a funny unit. I've been to the Grand Canyon a lot, and I'm not sure quite how to visualize what filling the Grand Canyon is like, but that sounds like a lot of magma. And this was picked up by many news outlets and publicized all over the place. And people that worry about prepping for, catastrophe use this as an excuse to go out and buy more freeze-dried food and things like that. And the National Park Service again published this cartoon. This is Yellowstone and Yellowstone Lake, and they have this really scary looking giant thing full of what's got to be liquid magma at a very shallow depth under the lake. It's like you don't want to jump up and down there because you might break the crust and cause an eruption or something. So this is all very scary, but in fact, that magma chamber is an area where there might be a few percent melt. So the enough magma to fill the Grand Canyon 11 times is a volume of rock whose seismic velocities indicate that there might be a few percent melt, as in this picture that I showed earlier. To me, that's not a scary, gigantic volume of magma as in the picture in the lower left. That's partially molten rock with a little bit of liquid in it. And if that liquid all collects into a reservoir, it could erupt, but I'm not worried about an eruption tomorrow from something that looks like what's in the picture in the lower left. To step into the layered mafic intrusion area, this colorful image is from the cover of the Geological Society of America bulletin from 1998, a paper by Irvine on the Skærgaard intrusion. And he envisioned, as do most people that have worked on it, a large mobile convecting magma system. And in order to convect, the magma has to have a pretty low crystal content. If it's getting up to 30, 40% crystals, it's too sluggish to convect. The viscosity, the effective viscosity goes up, so it won't convect like this. And he envisioned all sorts of processes, crystallization in from the margins, thicker on the bottom, Then on the top, as I said, convection, two-phase boundary layer flow, hydraulic jumps, density surge currents, plagioclase floating to the top, all sorts of things like that happen. Oops, sorry. All sorts of things like that happening. And again, this is based on examination of the crystallized remains of the Skærgaard. Nobody saw this happening. A couple of things I want to keep in mind, because I will return to it at the end of the talk, is the dimensions of this. This is a kilometer scale bar in the lower left. So before all this crystallization, this would have been maybe 5 kilometers top to bottom. We don't really know how deep it was because we don't see the bottom, but let's say at a minimum 4 or 5. And it's emplaced into basalts related to rifting of the North Atlantic, and various estimates I've seen indicate that it was emplaced anywhere from 1 to 2 kilometers below the surface. So very shallow, as in those pictures we saw earlier, a big active magma chamber at very shallow depth. So I will return to that. Now, one of the things that reinforces the magma chamber concept is the mapped boundaries of plutons. This is perhaps my favorite little pluton. It's up in the White Mountains of Eastern California. A really beautiful place, fun place to map. Here's the scale, 1 kilometer in the upper right. So this thing is maybe 4 kilometers across, semicircular, and it's very easy to envision one of those magma bodies crystallizing, and then erosion cuts down through it. And this is the cross section you would see. And for a long time, that's exactly how these were interpreted. My interpretation of that started to change owing to our work in Yosemite National Park. So this is a view from a place called Glacier Point, looking more or less east up the valley of Tenaya Creek. This is Half Dome. There's about 1,800 meters of relief from the top of Half Dome down to the valley floor here. As you can see, recent glaciation has just scoured the rocks clean. And almost every single rock you can see in this picture is part of the Half Dome granodiorite, a beautiful granodiorite with big hornblende crystals. I actually showed a picture of it in a previous slide, named after Half Dome, but all of this stuff is the Half Dome granodiorite. And the textbook interpretation of this has been published many times, and this figure is from a textbook. This is the map pattern of the intrusive suite that the Half Dome granodiorite is part of, and it is this light blue unit here. And it was interpreted as having, this is a sequential development of this final map pattern. And up in B here, it was interpreted as developing as a big blob of magma intruded all at once and crystallizing from the outside in. Now the scale bar here, this is a 10-kilometer scale bar. So this thing is more than 50 kilometers across. This is a gigantic blob of magma. And we went in there to try to, with modern uranium lead techniques, to try to figure out the time scale over which this would happen. It had to be really short for a mobile body like that to come in and then be intruded by a later body and pushed aside and so forth. That had to be a very fast time scale. And we found just the opposite. We found that this unit, the one I'm looking at here, was intruded over about a 4 million year period. We didn't believe the data at first because plutons were supposed to have one age. So we repeated it several times. And what we found was a very systematic pattern of younging from the outside in. The entire complex took about 10 million years to be emplaced. And we published these data sets in 2004 and proposed that most plutons are assembled in increments rather than coming in as large blobs of magma. That was extremely controversial back then. But I think it's been fairly well accepted for by at least the granitic rock community, perhaps less so in the layered mafic intrusion community. So that's when I started to question the paradigm of the big magma chamber. We went in here to look at vertical differentiation within this complex, figuring we have almost 2 kilometers of relief of vertical section. We expected changes in incompatible elements and compatible elements and xenolith abundance and all of those things. That was our hypothesis going in, and we found none of those things. An incremental emplacement kind of explains why that might be. So today, concepts of magma bodies, magmatic systems look more like this. Let's ignore C, that's a little bit out of date. On the left in panel A is a proposal by Peter Lippmann and others that a big batholithic system like the picture that I just showed of the Sierra Nevada consists of when it's active, consists of an upper crustal layer that's not melted, lenses of eruptible melt that will erupt typically in large ignimbrite eruptions. That melt is derived by crystallization of a great mass of partially molten material. The lower density melt collects up here where it's staged for eruption. So these would be magma chambers, and this would be mush or partially molten rock. And they draw it going down about 20 kilometers or more. So a gigantic section of basically transecting the entire crust of partially molten rock. A slightly more recent paper by Cashman and others, the Bristol group, Cashman, Sparks, and Blundy, has what they call transcrustal magmatic systems that are composed of a bunch of different magma chambers connected by dikes and so forth, and a large volume of mush around it. And they draw this as just coming up to the surface. So I got interested in the physics of this. I thought that it looks to me like these would take a lot of energy to sustain. And so I'm going to go into, for the rest of the talk, just looking at the energy budget for a system like this, if this is really how they exist, and what that would take in order to sustain it. So here is the actual figure from Cashman et al. You see this figure redrawn a lot these days. It's sort of the go-to figure for what crustal magmatic systems are like. And in that paper, or in the companion one where Sparks was first author, they showed the original geotherm before this system developed, and then what they call the mature geotherm on the right here, which is what the system looks like after it has developed into this mature transcrustal system. So I looked at that and decided to calculate how much energy it would take to push this geotherm up to here. And so that turns out to be a very simple integral of just the heat capacity, the density, the temperature difference between the two curves integrated over depth. And I just am doing it for the depth interval that they have in their paper down to 50 kilometers. But since it's this area in orange here, it obviously goes down below the figure as drawn. And so I'm going to give you a minimum. And so if you do that, you get a value of about 5 times 10 to the 13th joules per square meter. And that's about 50 terajoules per square meter. That sounds like a lot, and it is, but we're talking about a really big section of the crust. So what does that mean in terms of something more tangible? Well, if we say that the temperature of the mush, that big orange section in the figure that I showed before, is 800 degrees, and these are fungible numbers. I'm just choosing some. The results don't vary all that much with reasonable choices of these parameters. If that's 800 degrees, and we're driving this heating by basaltic magma cooling from a liquidus temperature of, let's say, 1200 down to 800 releases about 1 megajoule per kilogram, very nice round number, which is about 2.7 gigajoules per cubic meter. Okay, that sounds like a lot, and it is. Dacite magma, I'll be using that later in the talk, releases considerably less because it's cooler, and the enthalpy of fusion that's part of this number is smaller. So it's about 1 gigajoule per cubic meter, about less than half of basalt. So if we're driving this heating event by intruding basaltic magma, we have a number here in joules per square meter, a number here in joules per cubic meter. If we divide these two, we get a result in meters, and that is the amount of basaltic magma that you'd need to bring in to have enough heat to do this heating event that's shown on this figure, and that works out to 20 kilometers, give or take. So in other words, if you have an initial geotherm like this, and you want to heat it up to this, you need the heat content of 20 kilometers of basalt, and you'd have to inject that all throughout the column as dikes in order to heat this up. So that would involve thickening the crust by 20 kilometers. Now, if you were an engineer, here's the Lippmann and others crustal column, a little bit different, but same idea. If you were an engineer and you have the surface at 0 degrees, these melt lenses at 900 degrees, and then this big column of mush that let's say you want to keep at 800 degrees, you could very easily design a system that would consist of, I don't know, electric wires or steam pipes or something that could go through this to keep it at a constant temperature. That's how constant temperature baths work and so on. But the Earth doesn't have that. All the Earth has is magma and fluids if you want to heat things up. And so this heating has to, and sustaining of the heating has to be maintained by injection of magma. So I showed you how much you would need, 20 kilometers to heat up to that mature geotherm. Let's look in a little more detail at that. So I'm going to start out with a simple one-dimensional heat flow problem. So I have a sheet of magma. One-dimensional meaning we don't worry about cooling out the sides. The only cooling is out the top to the surface. We have heat coming in the bottom and heat going out the top. And I developed a simple little dimensionless number I call big M, which is the ratio of the heat coming in the bottom to the heat going out the top. Q is the surface heat flow. Q background is the background in the absence of any magma. It's generally small compared to Q. Density, magmatic heat release that I talked about a few slides ago, and then alpha is the accretion rate of magma. So that's how fast you're plating magma into this system, onto the bottom of the system. And in very simple terms, at steady state, if this parameter is greater than 1, the magma body grows. That means you're bringing in heat in the bottom faster than it's leaking out the top. So the magma body grows and you get a magma chamber. If M is less than 1, the magma freezes and you get an incrementally emplaced pluton. So let's plug some numbers into this. If I look at M equals 1, so balance, what does it take? Where is that tipping point where you go from just increments coming in and freezing to increments coming in and adding to a growing magma chamber? So that's at M equals 1. Solve for alpha. If we have dacite mush at 800 degrees at 5 kilometers depth and purely conductive heat flow, that's a big assumption, but that is the slowest mode of heat flow. So any numbers I give you would be significantly larger if we include hydrothermal convection, which we know happens. To maintain that mush, you have to bring in basaltic magma, or dacitic magma, I'm sorry, at about 10 millimeters per year. Which didn't sound like much. That's a centimeter. That doesn't sound like a lot, but that's math I can do in my head. That's 10 kilometers per million years. And so these systems are proposed to continue on in a somewhat steady state with eruptions happening and so forth for about, well, several million years typically for the examples I've given you. And so 2 million years is 20 kilometers, et cetera. And that's added on to the heat that it took to build up the big transcrustal magma system in the first place. So that's a very simple one-dimensional model. I spent several months working on more sophisticated two-dimensional models. For the calculations I did, there were some numerical instabilities I had to play with. This was a big effort, and it kind of came to the same result. So what I'm showing here are 3 panels. I did a bunch of models where I had magma bodies with their tops at 5 kilometers. So this is color-coded by temperature and contoured as well. Tops at 5 kilometers, and then various thicknesses. So I went from a 5 kilometer thick body to a 35 kilometer thick body. So top at 5 and bottom at 40. And then I also took this 5 kilometer thick body where the top is at 5 and bottom at 10. And then I moved it down and I did a series where I have a 5 kilometer thick body with its top at different depths. Heat flow is inversely proportional to the spacing of these isotherms here. So where the isotherms are close, there's a steep temperature gradient and heat flow is rapid. And you can quickly see that for the shallower one, the heat flow is much greater than for this deeper one on the right. heat flow out the top for this very thick body is about the same as for the 5 kilometer body, but there's more heat flowing out the sides because these narrowly spaced contours drape down the side there. So now we're going to get to the most visually boring but most important slide of the top of the talk, and this is the results from those models. So I've got 2 panels here. The first one is where I have bodies of variable thickness with their tops at 5 kilometers. As I said, that's sort of the standard depth at which people draw the tops of magma chambers. So for a 1 kilometer thick body, so this is energy and also kilometers of dacitic magma needed to sustain that, versus time, and this is 10 times 10 to the 5th, so that's 1,000,000 years. 1,000,000 years of sustenance for this 5 to 6 kilometer deep body takes about 13 kilometers of support, 13 kilometers of dacitic magma to come into that column. For the 5 kilometer thick body, takes about 16. For what's this, a 15 kilometer thick body here, 5 to 20 kilometers, it takes almost 20. And for the 35 kilometer thick body, this blue line, it only takes a little bit more. And that's because as you make it thicker and thicker, you're putting the deeper increments into rocks that are already hot because of the geothermal gradient. So the punchline is that for say a 5 to much thicker kilometer thick magma body, you need 15 to 20 kilometers per 1,000,000 years of support, of new magma added to keep it hot. On the right panel, I show 5 kilometer thick bodies. So that's this dashed line in the left panel with their tops placed at different depths. And so the dashed line is the same in both panels. That's about 16 kilometers per 1,000,000 years. And if I push it deeper and deeper, I need less and less. And for this deepest one, where its top is at 30 kilometers, I need, by this calculation, 4.5 kilometers per 1,000,000 years. So the problem of how much stuff you have to bring into the crust, doubling the thickness of the crust and so on in a few million years, becomes much less of a problem if we put things in deeper. And that's one of the punchlines of this, is that deeper magmatic systems avoid a lot of the problems of shallow magmatic systems. Nevertheless, these numbers all indicate significant crustal thickening if you want to have a magma system of the type that people draw active for some millions of years. The perfect place to look at this, what's happened here, is the Altiplano Puna Volcanic Center in the Andes, which has been active for several million years and is probably the most magmatically productive place on Earth. There are active volcanoes, lots of ignimbrite eruptions, and so forth. So what I've done here is drawn a line A to B through the Altiplano and then through the Altiplano Puna Volcanic Center and its volcanoes and down into central Chile here. And that cross section is here. It's pretty high. The Altiplano is about 4 kilometers. The Altiplano Puna Volcanic Center is more average, is around 4,500 kilometers, and some of the volcanoes farther south are even higher. But the key point is that the APVC is less than 1 kilometer higher than the amagmatic Altiplano here. The amount of magma needed to sustain a thick column of magma at shallow depth under the Altiplano for 1,000,000 years is given by this column here. It's 15 or 20, I forget which. That's how much excess elevation you would have if you piled all that extra magma on top. If it's isostatically compensated, it's still quite significant. It's extra altitude of several kilometers, and we just don't see that. And it's not because it's eroded away, because there is virtually no rainfall or external drainage in the Altiplano. Everything that gets out on the surface or in the crustal column stays there. And the crust is quite thick. It's, I don't know, under the Altiplano, 60 or 70 kilometers thick, I believe. So the excess topography hasn't been eroded away. It's just not there. And that tells me that there's something wrong with this model. Now, it might sound like I'm saying magma chambers never exist, and that's not true, because we do get 1,000 cubic kilometer super eruptions in the geologic record. This is an early morning shot of the Long Valley caldera in Eastern California, and you can see this big oval caldera. This is the one that had the big magma chamber under it in the 1976 paper that we now know is not there. This erupted maybe 600 kilometers of the Bishop Tuff, a rhyolite tuff that blankets the surrounding countryside and so forth. But there's no evidence of great crustal thickening before this eruption. I mean, the geologic history is pretty well known. It was 760,000 years ago. We can see that far back easily. There's no evidence that this thing bulged up dramatically as this magmatic system was assembled. So that's a conundrum, because it takes a lot of heat to maintain a shallow magma system. And the Bishop Tuff was supposed to have been erupted from around 5 kilometers. I personally am quite skeptical of that number, and that's something I'm looking at. Deeper magmatic systems help. This is a geophysicist diagram of the Altiplano Puno magmatic body, which is this thing that looks like a squished heart, this scary looking red blob here. This is an area where there is significant S-wave slowdown, and they, based on seismology and also magnetotellurics and some other things, this is thought to be a place where there might be 10, 20, maybe even 30% melt in places here. So it's still not a big mobile convecting magma body, but there's a lot of magmatic liquid in this thing if the geophysical inversion is correct. And the interesting thing is the top of this is at 15 kilometers below sea level, and the surface is almost 5. So that puts it basically 20 kilometers deep, not 5 kilometers, but 20 kilometers. And if I do the calculation for sustaining a magma body whose top is 20 kilometers below the surface, then I get a much smaller number, one that's much easier to believe. So I think that the answer to this conundrum is going to be that these things all happen at greater depths than we have supposed from our cartoons of magma chambers. I'm going to finish up by talking about the Skærgaard intrusion. So here's Irvine's picture again. We typically draw these things, and I did this for years, as just existing. You know, we draw this big magma body, this magma chamber, it exists, it's mostly liquid and it convects and all that, and that's what I taught for a long time. But I got interested in the problem, and this is partly from discussions with Rais, of how you can produce this starting condition in the first place. What kind of intrusion rates does it take to make a body that can be largely molten, and, you know, without just miraculous conception where it's just there? You have to start with a crust that doesn't have this and build it up. So I did some thermal models. So these are different thermal models. On these, time is on the horizontal axis, so it goes to 500,000 years, 500,000 years, and this is depth. It's in meters times 10 to the 4th, I'm sorry. So this is 2 kilometers, 4 kilometers, et cetera, down to 20 kilometers depth in all of them. So I'm intruding at a rate of, in this left-hand panel, of 10 millimeters per year. That's 10 kilometers per million years. So after the top of the body is always at 2 kilometers, and I'm always intruding the new bit at the top. I can intrude it at the bottom or the middle, and things don't change dramatically. And you can see where these new pulses of magma come in to average out 10 millimeters per year, and they heat things up a little bit and then cool down, heat up, cool down, heat up, cool down. The intrusion, meanwhile, is growing. The bottom of it is going down, down, down. So it's 5 kilometers thick at the end of this 500,000 year period. So that's not fast enough to make a Skærgaard. If I double it to 20 millimeters a year, now I've made a 10 kilometer thick magma body in 500,000 years. And toward the latter half of that, part of it is above the solidus. I've colored it so that blue is below the solidus, yellow is solidus. And then I arbitrarily chose 1100 degrees to be red, which is where I'm just arbitrarily saying that's liquid enough, you know, low enough crystal content that it can convect and so on and make what we would call a magma chamber. So this isn't fast enough. If I go to 40, I get a lot more rock above the solidus and a much thicker pluton, but we're still not in the red zone. If I go to 60 millimeters a year, which is 60 kilometers per million years, then I get a thin red zone here, a thin, largely molten zone right up near the top. But it's not several kilometers thick, it's a few hundred meters thick. If I go to 80 millimeters per year, then I get a big red zone. I'm making a big, largely molten magma body. If I want to match the Skærgaard, I just go over until the red zone is about 5 kilometers thick. And that happens at about 120,000 years. So I built a big convecting magma body that's 5 kilometers thick with more highly crystalline magma and solid rock that add up to 9 kilometers thick. So I've thickened the crust in that area by 9 kilometers in 120,000 years. That's 80 kilometers per million years. 120,000 years was the last interglacial. That wasn't very long ago geologically. The top of this thing is supposed to have been no more than a couple kilometers below the surface. Is it reasonable to say that we intruded 9 kilometers of magma that close to the surface in 120,000 years without some gigantic magmatic blister on the surface or something? There's something wrong here that we need to sort out. And my personal concept, and this is where I'm really going to get in trouble, is just saying that our concept of these as big convecting magma bodies is just incorrect, and that layering and so forth formed by other processes. So I'll finish by saying that we need a magma chamber concept that is consistent with all the data we can throw at it. I got interested in this from the geochronology point of view, but I think that any concept of a magma chamber, especially a shallow one, has to satisfy geodesy. You have to move things at rates that are reasonable, not inflating 9 kilometers since the last interglacial. Geomorphology, if these things are inflating, they should leave a big signal, and we don't see that. Seismic tomography, volcanic seismology, gravity, heat flow, and of course, petrology. These all have to fit if we have a consistent model of what a magma chamber is. So to summarize, I'll show you, this is, we're talking about Pluto's realm. This is painting Orpheus, what's the title? Orpheus Before Pluto and Proserpina by, it's painted around the 1600 by Jan Bruegel the Elder. And we're arguing about what does this look like? I hope it doesn't look like what a magma chambers look like. I hope not like this. And we're arguing about what depth they are at down there in Pluto's realm. And so my summary is that the concept of a shallow, highly molten magma chamber rarely applies. I'm not saying it never does, but I think it rarely applies, partly just because geophysicists cannot find them. Many magma chambers, as imaged in redite and blueite, you know, a big red blob under a volcano, as I showed for Yellowstone, are barely molten at all. So this has to do with that definition of magma. We really need to settle that. Sustaining shallow magma bodies requires an enormous influx of magma, and this sort of inflation is not recognized in the geologic record. Putting magma bodies deep or in extensional environments, something I didn't talk about, solves many of these problems. And finally, it is difficult, maybe even impossible, to build shallow big tanks of magma without catastrophic events like Sudbury, like a meteor strike that can instantaneously melt huge volumes of the crust. Building them by the kinds of processes we have on the Earth today is just thermally really difficult. Maybe I made mistakes in the calculations. If anybody sees flaws in that, I would love to talk about that, because I'm open to changing my mind if the physics changes. But based on what I've seen, this is a really difficult problem that requires some rethinking. So I'll leave it there, and thank you, and I'd love to answer some questions.
Thank you so much. That was a really brilliant talk, and you can see by the audience numbers, both on Zoom and I think on YouTube, that I think everyone's really appreciated it, and I can see many hands going up already. So Lou, I think you got your hand up first, so you should be able to.
Okay. Okay. Hi, Alan. It's great to see you again, and a terrific talk, as Grant said. I wanted to say that regarding the definition of magma, of course, it's going to be different for everybody, right? That there isn't a consistent definition. But the way I see it is that I like to use the word magma to distinguish it from melt. Melt is purely liquid silicate melt. But
Agreed.
Magma, to my mind, is melt plus crystals plus vapor plus bubbles plus cargo of all kinds. So it is a jumbled up mess. So that's the way I use the word magma. And your second slide, where you showed a blank screen and you asked us to imagine or draw in our minds what a magma chamber looks like, what I would have done is drawn the thinnest possible line I could draw all the way from left to right on the screen there. And that's what I think a magma chamber looks like. I do not have the concept of a huge tank of melt or even magma. Rather, I think they come in as thin sills, probably full of crystals. And that's how I think mafic layered intrusions are built up, rather than the Skærgaard model of Irvine, which some people still insist upon. Right. The Bushveld community is moving very much away from that these days.
Okay, I'm not going to step into that one right now, but I think that's an enlightened viewpoint, and I support that. Also, I agree about magma. The point we made in our EOS opinion piece was that we define magma as that mixture of melt and crystals and so on that is mobile enough to move on volcanic timescales so that it can intrude and so forth. You know, you could deform that 98% crystal, 2% liquid stuff on very long timescales, but we made the connection that it's kind of like using the same term for a reservoir and an aquifer. You know, those are both things full of water, but they're completely different in their behavior and so forth. So I'm afraid somebody's going to get in big trouble by saying, oh, there's this gigantic amount of magma under Mount Rainier and housing prices tank and so on. Because the USGS already got in trouble in Mammoth Lakes in California for predicting an eruption in that area, and housing prices tanked and everything, and they got slapped really hard for that. So it'd be nice if we had a common definition. I mean, it's such a fundamental thing in petrology, the fact that some people use it for something that's 2% melt and some for something that's 100% melt. That's too much slop. But nobody seems to care except me, so I'll get off of my soapbox.
Thanks, Lou. Great question. John Clements, I see your question. Thanks for joining us, and you should be able to unmute. And you can go ahead.
Hi, John.
You're breaking up there. I don't know whether it was me or you that's got the problem. I'll try and move to a more stable place. Alan, can you hear me okay?
I can. Good to see you.
Oh, perfect. Yeah, nice to see you too. And I'm very glad that someone is challenging some of these magma chamber ideas. I guess I'd like to make two comments and ask you what you think about them. The first one is something that Alex Kister's alerted me to when he read that Cashman et al. Paper and saw the cartoon of the crustal scale magma columns. And he said, if you were in any kind of convergent margin setting, that wouldn't last 5 minutes. It would be sheared out. And you could never establish or maintain such a partially molten system. Mind you, if it were only of the kind of 1 or 2 or 3% melt, then we'd be talking about a different thing. But the way it's been put forward by its proponents has been much larger amounts and much bigger bodies of eruptible magma distributed through it. So that's the first thing. The other one is, and it's relevant to Lou's point as well, the vertical extent of these intrusions. Recently participated in a paper headed up by Neil Phillips in Australia. We've got a thing called the Strathbogie batholith. I think you've seen it.
I've seen it, and I
Yeah.
recognized an awful lot of that. Thanks for that field trip. Yeah.
And the thing is that Neil has now successfully delineated the roof and the floor of that batholith. Now, to remind people who don't know, we're talking about something knocking on 40, 50 kilometers by 100 kilometers in size. And nowhere is it thicker than 350 meters. So a very thin.
I think that's great. That's our interpretation of a lot of the work in the Sierra Nevada batholith in California. It's just that the wall rocks are pluton, so it's harder to make the distinctions like you did in Australia. Yeah.
Yeah. So I think maybe we're trending in the right direction in recognizing that these things we've been thinking of as magma chambers really aren't all that extensive and are not. The system may be long-lived, but the individual bits of it are probably not. And of course, there are differences. Those Australian rocks that I've just been talking about, they probably were quite short-lived events compared to, say, Sierra Nevada, where you've worked. But it's all still, things are a bit self-similar. You know? Maybe
I agree. I love that paper. I love Neil's paper. That was a beautiful piece of work. Yeah.
Yeah, it's it's something very few people are going to do, to go out there and map in a lousy. Well, you've seen the terrain. It's not so easy to map in a place like that. But you've got to. I think we've got to try it.
Well, you know that round pluton, the Sachem flat pluton that I showed, I said is my favorite little pluton. That had been mapped actually by my office mate in graduate school as a big beer can shaped thing that goes quite deep and so on. And at the GSA meeting in Las Vegas a few weeks ago, a group from Wisconsin showed gravity data that say that it can't be thicker than maybe 300 or 400 meters. Very consistent with what you were saying. So I think laccoliths need another look. The link between laccoliths and big bodies of granite need another look, because we can see how laccoliths form, like the classic ones in the Colorado Plateau. You can actually trace the filling of those things by tilting of the wall rocks and paleomagnetics. They stack downward. The earlier pulses are bowed out by the later ones and all. And I think that model might apply more broadly than people realize. Yeah,
I'd even suggest it's got pretty important implications for some economic geology, because there are kinds of ore deposits that are thought to be magmatic, and you need absolutely massive amounts of pluton in order to produce this tiny little bit of highly fractionated ore-bearing cupola, as they want to call these things. And I think this is open to a lot of question these days.
Thank you, Jason. Thank you so much for that interesting question. We've got another question here from Merrily Tao in the audience. How did the big tank of, I presume, magma with low volume melts and high VSVP get there below supervolcanoes if it did not arrive as a liquid or slurry?
I agree with what John said about many plutons being assembled as sheets. You know, we might call them sills, but, you know, depending on the kinds of wall rocks they're in, but some horizontal sheets, but they're fed by dikes. And above the Yellowstone plume, it's easy to imagine that you have lots of dikes coming up. It is an area of very high heat flow, but all they see is the VP-VS ratio averaged over fairly large volumes. And so dikes, you know, heating the wall rocks, dikes with a decent amount of melt being averaged in with wall rocks that have no melt and so on can give you those same signatures. If I had another life, I would study seismic tomography so that I could understand that better, but I don't. So I do the best I can, but I think that's a very fruitful thing. We ran an AGU session in about 5 years ago where we invited petrologists and geophysicists, and we interleaved the talks so that it wasn't like morning geophysics, afternoon petrology, and we interleaved them. So try to get people to sit through each other's. And I think that was pretty successful. And that's another thing we need is to get the petrologists that work on the rocks and the geophysicists that image them together. I will also add that the transcrustal magma system that John pointed out would have a pretty low viscosity and get sheared pretty easily. That would show up like crazy in its geophysical footprint, because you'd have very slow S waves from the moho to the surface. You'd have a huge heat flow anomaly and so on. So I don't think that's viable. So
thank you, Alan. You've made the geophysicists in the audience very happy there, raising their arms in agreement. I see Race has got his video on, is unmuted. So Race, would you like to come through?
Yeah, if possible. Yeah, Alan, thank you very much for your talk. Really interesting and inspiring as usual. I'm applauding the part about the crystal marsh, that Cashman. Totally agree with you. And as you know, totally disagree with you about the magma chambers. I do see it totally different. And you know that you are not addressing a few things, which I'm always talking about this. So you are not talking about them. I will not bring it here, but you know that you have a big problems. But my question here is, I'm not quite sure how you really produce these large igneous provinces in your large eruptions in your model. If it's just seals coming and they're solidifying very quickly, so how you can these big magma which erupts in a matter of 6 days or something like in the Bishop.
So you're talking about silicic eruptions or large igneous? Okay.
Yeah, maybe. Okay, let's take it.
I intend to critically examine the information about the depth from which these eruptions come, because my guess for much of igneous petrology is that the action is in the lower crust or mantle, and that not much happens at the level at which we sample these things. And I would not be surprised if 10 years from now we find out that these big ignimbrites are actually being sourced from magma bodies in the lower crust. You can theoretically drain a mush by diking. You could have a large volume that has, let's say, 10% melt. And by diking, John Eichelberger did some simple calculations on this and showed that you could theoretically drain that to get the silicic liquid out on sort of those sorts of timescales, a week timescales. But as my calculation showed, it's a lot easier to put these things together in the deep crust than in the shallow crust. I mean, I think the physics is so clear that you just can't build these things in the shallow crust without just ballooning the crust like crazy, because you have to pump heat in so fast to build up a magma body. So my guess, and that's all it is right now, or hypothesis, is that the action's happening in the lower crust. So things like the Bishop Tuff and the Yellowstone Tuffs and all are coming from, they're being built and staged in the lower crust and erupt from there. People say, how can you get such a beautiful circular caldera from that? And I've looked some at mine collapses and karst collapses and so on, and have a very irregular chamber collapse. Actually, people in Johannesburg probably know much more about this than I do. They tend to round out as the collapse propagates upward. There's probably some sort of minimum work principle or something to get the minimum area around that. So I wouldn't be surprised if you could produce the kinds of calderas we see at the surface from an eruption from a deep chamber. Deeper. It doesn't have to be 3 or 5 kilometers deep.
Mm-hmm. Okay, I see. Just Grant, if possible, just 2 comments. We've done some work with Catherine Annan, and perhaps I mentioned that she basically done the same calculation as you did, and she got absolutely the same results. That tells me that you're right with your calculations. And but we also did, as you inspired us, we did the job with the Skærgaard intrusion, modeling of Skærgaard intrusion, and it's this paper now in review now. And I think that it will be interesting for you, because we came to totally different conclusions, which from what you are showing here. And
that will be
interesting. Yeah. So I think we'll discuss this. Anyway, thank you very much. Great talk.
I did the Skærgaard calculations yesterday, so
okay.
I'd like to see yours. It's possible.
We've done almost 3 months trying to really to reproduce that. And I think we've done it in a very nice way. So I'm very happy with results.
One other comment to follow on that I did not emphasize is that all my calculations were for completely conductive cooling, which is the slowest, which minimizes the problem. If there's any convection, and we know there was at Skærgaard, for example, cooling is much faster and the problem gets worse. So
yeah.
I was trying to make the most conservative estimates I could, but I'd love to see that.
Okay, great. I'll send you. Thank
you.
Another
Geotalk, right? Sounds like you're in for another Geotalk soon, huh?
Yeah. Yes. Thank you.
All right. Sue, I think you have a question from the audience.
Hi, Alan. Thanks for a really great talk. I really enjoyed it, and good to see all that geophysics. I'm a geophysicist. So what I wanted to ask is, it seems like you're actually pushing the problem down into a staging chamber, in a sense of how much melt is there, or where is it? And I like that, you know, by pushing it down, you're disturbing the geotherms less, and it's easier to have a bigger amount in there. I was a little confused by your calculations, and I'll have to look at them because I'm used to thinking in terms of volume and not one-dimensional units. So that just kind of was interesting. But so how big and what evidence would you say we can look for as geophysicists for the staging chambers? Because we think we see some under the Bushveld, and we're actually working on a paper on that right now. And I'm just curious what your thoughts are on the staging chamber question.
Well, again, if I could, I would study tomography and seismology in general so that I could understand it better. But, you know, there are bright spots down deep in the crust in various places that show up in receiver functions and so on that people have interpreted as magma bodies. I understand the problems with seismic waves bypassing slow areas, you know, working their way around slow areas so that slow areas are harder to see. And I don't know. I just wonder if multi-technique studies might be the best. Matt Pritchard was lead author on an article in Elements that we put together about 6 years ago, where he looked at exactly this question. How much magma is there? He was looking shallower, but how much magma is there? And combining seismology and magnetotellurics and a few other things, and modeling of INSAR, you know, uplift rates and so on. I thought it was a very well-reasoned approach at bringing in more than one geophysical technique to try to answer that. Petrologists need to come up with better barometers. We need better ways to tell the depths from which things erupt and the depths at which plutons are emplaced and all, and we're just failing. There just aren't things for doing that. So I can't answer your question, but I think that one approach is to get petrologists and geophysicists together. We need conferences where they sit around and talk about these things at a level that the other group can understand what you're saying. And we might be able to brainstorm some ways to look at this. So let's do it.
Great. Thank you, Sue. And Alan, thank you. I think that's a great idea. Perhaps we should think about doing that in South Africa, here in Johannesburg. And you can then come out and get to the Bushveld too. So that sounds like a fantastic idea. So thank you very much once again. I think we'll end off the questions there. But let me just remind you then of the talk next week, which is going to be given by one of our newest staff members, Kimberly Beaton. And she'll be speaking about amphibolite facies metamorphism in the lower Wits supergroup, exposed in the Vredefort Dome, and the connection to the Ventersdorp large igneous province. So we'll be speaking about large igneous provinces from a different perspective next week. So we'll see you all next week. Thanks for joining us. And Alan, thank you once again.
Yes, if I could just thank the audience. Those were brilliant questions. I appreciated that. I'd love to continue this by email or future Zooms or something if anyone is interested. And I can send a reprint or two of some of this stuff if anyone is interested in that. Just drop me an email.
Fantastic, Alan. Maybe we should organize a geo discussion group where we can all sit around and discuss one of your papers, and perhaps a complementary paper that takes it from a different view. Maybe when Race's paper comes out, I think that might be a good discussion group to have.
Excellent.
Great. Thanks, everyone.
Thanks again, everybody. Okay.